All right, good. So now that we get that going, so the last day we were dealing with motion in one dimension. And we talked about the what we call the motion equation, right? And we said that once we're dealing with constant acceleration, right? Constant acceleration. You will hear sometimes the textbooks say uniform acceleration, right? So instead of constant, you have uniform. Then we can actually use the motion equations. I don't know if you can remember them. The motion equations to solve problems involving, a body or an object moving in one dimension. And because I think I mentioned too that when you're dealing with vertical motion, something being thrown up or something being dropped, that's also one-dimensional motion. And interestingly enough, the acceleration of a body, whether being dropped or whether it's being thrown up, and the body is going to decelerate or slow down, it's going to either accelerate uniformly or decelerate uniformly. And the acceleration or deceleration will be g equal. And I remember, I think somebody in the class was asking whether the g means grams. And I was saying, no, this g means acceleration due to gravity, right? Gravity. And well, depending on where you are on the Earth, the value varies slightly. At the equator, it's around 9.8. Sometimes you see people say 9.81, right? Meter per second square, or if you see it's written like this, meter per second square, like that, right? They're in the north, sometimes they just round it off to 10 meter per second square, right? Because it's a little higher as you move away from the equator, right? There's a little science behind that, right? Because of the distance from the center of the earth, right? For those of us, if you understand how the earth, the spherical shape of the earth, the equator, let me say, okay, this is the center of the earth. The distance to the equator is very short as compared to, let's say, somewhere in the north. The distance from the center to that point on the surface of the earth is going to be a little longer, farther, sorry. Right? And for that reason, the acceleration due to gravity there is going to be a little greater, right? Yeah. Yeah, we're not getting into that. I was explaining, I think we were talking the last class. It's the reason why they want to build space stations here, because that 0.1 and 0.2 difference you see there would mean that the engines of the rockets and so had to be so much more powerful. Well, until these famous men like Elon Musk and there's this new guy now. Well, Amazon has joined the race, and there's a guy called Richard Branson, Sir Richard Branson. They decided that, look, I mean, right now how they're launching rockets, they usually launch from the ground. And these other guys said, no, let's take the we call it payload, like, right? As high as we can go and launch from up there, right? And that has been working to some extent, right? So they're flying whatever has to be taken to space. They're flying it as close as possible to where they, the threshold, like where they go get into space, and then launch from there, right? And it's actually more economical. the engine of the rocket doesn't have to be that powerful and all of that. Anyway, that's not our course. I just wanted to highlight what G is, right? And when we are dealing with vertical motion, we actually have um, constant acceleration. And when we say that, we are actually assuming that um, a resistance, because a resistance can really affect how something fall or the rate at which something climbs in height vertically when you project it vertically,
Sir,
right?
excuse me.
Yeah.
Sir, so G, which is acceleration due to gravity, is 9.81.
As I said, it varies on different parts of the earth. Um, Sometimes we can, well, if in the course, if you have to use G, I will tell you what to use as the value, right? So don't worry about that. I will tell you, use G as 9.8 or 9.81 or 10. I will tell you.
Alright, good, good.
Yes, it is the least, right, at the equator. And if you want to know why, just ask one of the AIs. Why is acceleration due to gravity, or the what they call it, gravitational field strength? Why is it the least, right, around the equator, but more to the north and south? Um, it's it's a little higher. You can ask an AI, and it will give you an explanation, right? Um, yeah. And any specific reason why you ask that question?
Sir, just because I want to know if there's the standard value of G.
Yeah. Well, I will tell you what to use as a standard value, right? Don't kill yourself. Yeah. So as I said, because if you were to throw up something vertically, or something is to be projected vertically, or something is falling down vertically, the motion equations will also apply, right? The only difference now is that the acceleration is going to be G, right? It's going to be acceleration due to gravity. So keep that in mind. So anytime you have a problem, right, that involves motion, well, all you got to do is um, use the motion equations, right? And we'll talk, of course, when instead of using the motion equation, um, what else we can do, right? And we're going to get into that later this evening. But as I promise you, I think I promised you that, look, we're going to do a couple of examples, not too many, just about two or three of them, maybe four the most, that involves the motion equations, and they're going to be very simple, right? Let's see if I can try to cut some simple ones. Um, Look at this one. You're seeing this one? So it's saying that a stone is thrown vertically upward from the top of a tower and hits the ground 10 seconds later with a speed of 51 meter per second. They want you to find the height of the tower. Right? So let me give you a little diagram as to what's going on. All right. Oh my, what's going to happen there now? Good. So you can see this, right? So we're saying that, all right, we have a tower. It's kind of draw the tower there, right? And you project this thing vertically upward. And of course, you're going to argue that, man, it has to be at the very edge of this tower. Because when it's falling, my very fall back right on top of the tower. But we're saying it misses it and it falls just parallel to it and it hits the ground with 51 meter per second. Right? So notice nothing was said about what was the speed that you project the stone with into the air, right? So you don't know the initial velocity, right? What you know is v. You know where it hit the ground with 51. Again, we use 9.8 as the acceleration due to gravity. It took 10 seconds to reach the ground again, right? And then we don't know S. We don't know this. So what we got to do now is look for an equation that will tell us the unknown given what we know. Right? So we know V, we know A, we know T, but we don't know S. And right away you see, remember this equation, right? You remember that equation. So basically, we're treating downward as positive. As I said before, you decide whether you want to treat downward as positive or whether you want to treat downward as negative, upward as positive. In this problem, it seems because this stone it was thrown up a little and then it came down, and if the vast majority of its journey is coming down, right? It's coming down. Therefore, the author says, look, let's treat down as positive, right? So the V is positive, notice. The A is positive. Well, time is always positive, right? So we need to find S, right? So S equals Vt minus half AT squared. You substitute all the numbers. V by T, which is 51 by 10, 510, minus half A, right? Times T, right? So half AT squared. So half by 10 squared. 10 squared is 100. 100 by half is 50, right? Times A. And when we work out this, the arithmetic will tell us 20. So our tower so happens to be 20 meters high. Right? Very often when you have to use the equations, they're not very difficult. They're not very difficult. When it can get difficult is perhaps if you're dealing with maybe more than one body being thrown at the same time, right? So I'll do one like that. You get this one though? Is this one difficult?
Sir, this is what the layout usually looks like in an exam setting. Will we be given the relevant information, or we'll have to figure it out?
I might not tell you what V is and what A is and what T is.
Okay.
I'll describe the
Understood.
problem. Yes,
I understand. Thank you. Just
yes,
confirm.
yes.
As if you'd given me then, it would have been perfect. We would have loved it.
Yeah, I can't do everything for you, right? So that's the nature of the real world, eh? And these are oversimplified problems. As you see, we didn't take into account air resistance and all of that, right? Um, if we take into account all of that, things get more complicated. But remember, we're just doing a basic physics course. If you're to get into these other things, well, it's in a more advanced course, you know? Yeah, so the problem might be described to you, and you got to pick out, well, and reason, right? Um, okay, now that you mentioned that, if I tell you that so an object was dropped from a certain height, right? An object was dropped right away, you got to know that, you know what? U equals 0, right? Because when something is dropped, it means that initially when t equals 0, the object is at rest. It's in your hand, right? And you probably let it go, right? And when you let it go, then is when the time starts to count, right? So if it's falling, well, then it's going to change velocity because acceleration is going to act on it, right? And if you want to know, well, what's the velocity after 5 seconds? Well, you use v equal u plus at, right? You know u is 0. You know a is going to be, okay, let's say use 9.8 by, and let's say 5 seconds. And so your v is going to be this by that, whatever it works out to be. So you got certain keywords. And there's where a bit of reading, I gave you some notes. You can do some reading and kind of try to figure out the kind of language we use, right? Um, and then you'll know that, you know what, when you talk about something is at rest, what it means that it has 0 velocity, right? Something it's moving, it's accelerating uniformly. What that means, say, that means the acceleration is constant, right? And the motion equations apply, right? Again, when we talk about air resistance, if I say, look, in this problem, neglect air resistance, because air resistance is variable. So sometimes you ever throw up something like, I don't know if you all play with frisbee, and maybe an object that offers a lot of resistance, or I shouldn't say the object offers the resistance. It's the air that offers a lot of resistance to an object. Maybe it's flattened in some way, and you notice it's going from, it's going this way, it's going this way, it's going this way. So what's going on here, man? Right? Because the way air is acting on it, is causing it to not fall, to the ground at 9.8 always. No, it might not be this, right? And that's when a lot of the problems for 9.8 to hold, the object has to be maybe spherical, like a ball, and it has to be a very small surface area, and possibly volume, right? The minute you start getting a big object, air resistance is going to change that 9.8, the rate at which it falls, right? As a matter of fact, there's something called terminal velocity. Y'all probably saw this kind of thing in the movies, and so people jumping out of aircrafts and so, right? And what happens sometimes is that people will jump out of an aircraft, maybe with a parachute, or there are these people who would they don't deploy the parachute right away. They'll enjoy the jump. They're very experienced people, right? So they'll go at a certain height and they know, look, for probably 500 feet or maybe 1,000 feet, I can fool around a little. So they actually don't deploy the parachute, right? And what would happen is that the air resistance will be so much on their body, right? So let us say that, all right, when they achieve a certain speed, right? When they achieve a certain speed, the wind below them, then the air below them, is equal to their weight that they're falling with, right? And whatever speed they're falling at, they're not going to accelerate from that, right? Let me quickly get an estimate for you. Terminal velocity in air. I just want to see a rough figure. I'm not seeing a rough figure here. Some of them they're giving all kinds of. Well, this particular reference here says about 55 meter per second. Translate that to km per hour. Anybody's doing it for me? Multiply, what we have to do? Multiply 55 by 3.6, is it? Hmm? Anybody doing it for me? Yes.
Sir, I got 198.
Yes, that's the speed. So this is just a, remember, it depends on the condition. It has to do with, the moisture content of the air and so many other things, right? Temperature and all of that, right? This is just an estimate somebody gave here on the internet. So yes, that can happen. So they come to a point where they fall down, they're falling, right? And they reach that point where the resistance of the air equals the gravitational pull of the earth. So whatever speed they're falling at, they fall at that constant speed. Yeah. But we're not gonna get so complicated, right? We're not gonna get so complicated. Let's deal with another one. Maybe this one is gonna be a little harder. Um, I didn't want to highlight it. It might be. All right. I'll still highlight it. Okay, look at this one. One second. I know I'm dazzling your eyes. So look at this problem. And here is where it might get a bit complicated for you, right? And I wonder whether y'all did any kind of mathematics that will help you with this. But I'll see. If the mathematics is beyond you, I'll have to take it out, right? So they're saying that, okay, one ball is thrown vertically upward with a speed of 14 meters per second. 2 seconds later, another ball is dropped from the same point, right? So one is pelted upward, and the other one is dropped from that point, right? So they want to say, well, all right, find where the two balls meet. So what's happening here really? One is thrown, ball is thrown vertically upward with a speed of so all right. It looks like it doesn't say here, right? But it seems as though it's some height. So one is thrown upwards, one is thrown upwards, right? With 14 meter per second. And then 2 seconds later, one is dropped, right? From the same point here. So one is thrown up. 2 seconds later, one is thrown down, right? They want to know, well, where the two balls will meet, right? In other words, the two of them must have the same displacement from the starting point, right? So there will come a time, sometime in the future, where these two balls, okay, let's say this is one of them. You use like an object there, you know, one, and maybe put two on this one. One and two, right? So at some point, maybe down here, somewhere here, the two of them, one and two, are going to be the same displacement, right? The same displacement from the starting position. That's what you're saying, right? You think you understand what they're asking?
Yes, sir.
Good. So, let me move this aside. I'll bring the solution for you here. Good. Good. So here's the solution. So they're basically saying the balls will meet when they have the same displacement from the starting point. And I just explained that, right? When the two of them, well, this one goes up, comes down back, right? And it's possible that because of the speed of this one, when it goes up there and it's coming down back, it might very well have remember at this starting position here, it's going to have 14 meters per second. Remember we said that? If you throw up something with 14 meters per second, it's going to go to a maximum height, stop, and come down back. Because you might be asking how this ball that you throw up will meet this ball that you release later on. Yes, they could meet. The reason why is that, first of all, you will allow some time to elapse. And secondly, when this ball goes to its highest position, come down back, it's going to have a speed of 14 meters per second when it reaches back this original position, right? So while this one has a head start in a way, it doesn't really have a head start because it's dropped 2 seconds later. But this one, when it reaches back here, it actually has 14 meters per second to start with, right? So it can very well meet up that second ball, right? Good. So this is the mathematics behind it. Just give me 1 second, right? Yeah. Yes. So what we're going to do, we're going to break the motion of these two balls into two parts. And rightly so, right? So a couple of things, right? So they say that if the time taken by the first ball to achieve the displacement is t seconds, the time taken by the second ball is going to be t minus 2. And why are we saying this? Because the second one was released a little later, right? So if t seconds is the time that the first one has been in motion, then the second one is going to be a little later, which is t minus 2. See if you get me up to there.
Yes, sir.
That makes sense? So one of them, the first ball, we're using that like the reference ball in. And the time that it's in the air, we're going to give it t seconds, right? The one that is released 2 seconds later is going to, well, we're going to take that time to be t minus 2 seconds, right? Good. So notice they also, they stipulated a certain convention here. They're taking up as positive. Remember I said you have to decide that, right? You have to decide that. Whether up is positive or down is positive. You can decide that. You can change this whole problem and say, look, I want no up to be positive, right? But this writer says, look, I'm going to take up as positive. Good. So for the first ball, forget that second ball. Don't go here yet. We're at the first ball. So what information we have? U is 14. It's thrown up with 14 meters per second. A, notice they use negative 9.8. The reason why is that we're taking up as positive, but acceleration due to gravity is acting down. So the acceleration is going to be negative, not positive. Right? The direction of this, the pull of the earth is downward. And if we are taking upward as positive, well, then acceleration, because it's acting down, we're going to take it as negative 9.8. I think you get that. If you don't get that, let's make sure we get that. Time, as we said, for the force ball, we're going to take it as capital T. S equal D. We don't know this. We don't know that, right? So we're going to use a formula, S equal UT plus half AT squared. So this is the D, right? We don't know that. So that can be written in terms of, well, our U is 14, T is capital T, half AT squared. Remember, half of 9.8 is 4.9, right? So what we get here is what we call this is an equation with two unknowns. We don't know D and we don't know T, right? Two things we don't know. And whenever you have two unknowns, you have to get two sets of information to solve a problem like that, right? So we're going to look at the second ball now. We can't solve nothing here. Got too many unknowns and too little is given. So we're going to look at this second ball now. This ball was dropped. Remember, we use the word drop, meaning initially you didn't give it a velocity. You had it in your hand and you just lose it. So the velocity at the beginning, or the initial velocity, is 0, right? Again, we are treating downward as negative, upward as positive. So A is going to be negative 9.8. T, we said it was dropped 2 seconds later. We're going to use the first ball, the time that the first ball was released, as the reference. So the time is going to be T minus 2. And again, we don't know D. The two of them, where the two of them meet is D. We don't know where. We got to find D. So again, we use the same equation, D equal, right? Well, remember UT, remember U is 0. So this whole term gone. So all we're left with is half AT squared, right? Which is minus 4.9 T minus 2 all squared. So D is equals to this and D is equal to that. So if both of them are D, then we can put this and this equal, and that's what they did here, right? And what is happening there now is, have you, well, that's a question I need to ask. Have you done mathematics to that extent where you can solve what we call a, well, in this case, it's like a quadratic equation almost, right? Y'all did that level of mathematics?
No,
No.
sir.
Sir, many years.
So yeah, many years ago, sir. Just
Many
we
years.
now I'm starting back classes. It's very much.
Oh, okay. I suspected that this is going to go on to something complex, where the mathematics is very heavy, right? I'm only going to solve out this one, but I'll try to avoid a situation that will call for heavy mathematics, right? So maybe we can probably try this one. Just what? I think this is what the let's draw it. 14t minus 4.9 t squared, right? I should be using capital T, is equals to negative 4.9 t minus 2 squared, right? So we got to solve that, right? And that's quite a bit of work. But let's see. Remember, this writer thinks that, well, you know a lot of mathematics, so they just jump to the solution here. So let's see if we can do that here, right? I'm thinking if I can take out. Let me remove the bracket here. So I have 14t minus 4.9t squared equal to, when we remove this bracket, we'll have, oh, we can't remove the bracket. We got to do the powers of force, right? And this is going to be t squared minus 4t plus 4, right? And then we have to multiply everything by minus 4.9, right? So we'll have 14t. The mathematics is going to be too complex for you. I think I'm wasting time. Minus 4.9t squared plus, could somebody multiply 4.9 by 4 for me? What is going to be? 19.6.
19.6. Yes.
Okay, t minus 19.6 again. Good. So this 4.9t squared, this here is going to cancel with that, right? And we're left with, I'll bring this over here and bring that over here. So I'll end up with 19.6 is equals to 19.6t minus 14t. So we get 19.6 is equals to, what is this? 14 from 19 is what, 5? T?
Yes, sir.
So
5.6.
t is equals to 19.6 over 5.6. How much is that? Will that, they have 3 here, 3.5. Is that it? Right?
Yes, sir. That's it.
So after we have found, yes, what do you? Somebody was going to ask something? Yeah. So now that we have found t equal 3.5, we need to put it back now in one of these equations so that we can be able to solve for d. Remember, that's what we're doing? So d, any one of them, you want to use this one on top here? So d is equals to, remember we said 14t minus 4.9t squared, right? That's from equation 1. So it's equal to 14 by 3.5 minus 4.9 by 3.5 square. And they said it should work out to give you minus 11. Now, how do we interpret this minus 11 here? Remember, we said that up is positive and down is negative. So the fact that this is minus 11 meters down, right? Sorry, I shouldn't say down. Minus 11 meters means that the two balls meet 11 meters below, right? Below where they were projected or dropped from, right? Dropped from. That's what that 11, this minus 11 means. Remember we said negative is down, positive is up. So where you have 11, minus 11 means that these two balls, they actually are 11 meters below that point from where they were dropped. That's where both of them are the same height. They meet there, right? Of course, one can overtake the other two. If, well, that's a good question. That's a heavier question now. Will one overtake the other? That's an interesting question. I'm not going to get that far, right? It's a question for a more advanced physics student.
Sir, excuse
Yeah.
me. I have a question.
Yeah.
So you have 14T. What is the T for, really?
T is the time
Is
that force ball. T is actually the time for that, how long that force ball is in motion. If you go back here, right here where it says, if the time taken by the force ball to achieve the displacement or the distance where the two of them meet, we calling it T, right? It's the time that force ball takes to meet up the second ball then. Right? So the force
Sir, where
ball
you
will
getting
take,
4.9 from?
say it again.
Where where did you get 4.9 from?
This 4.9 here.
Yeah.
Yeah. Well, half of A is minus 9.8. The half of 9.8 is 4.9. Yes?
Gotcha.
Yeah. But you have to know a bit of mathematics here. I'm not sure, I may have to try to avoid any kind of complex mathematical problem.
Please
You
and
know?
thank you. Highly
Yeah.
appreciate it.
Yes, I'm smelling plastic burning. Sometimes you gotta wonder now, with the dry weather. And I hope, probably it's a neighbor burning garbage. Yeah.
We're just
Right. So
checking.
can I move this? Can I move this? Good. So what I want to divert into now is how we can use graphs. How we can use graphs to solve problems in kinematics. Right? That's where I want to deviate into now. And sometimes the use of a graph is a little more um, well, it gives you an easier way to analyze problems, right? Um, and you can get so much from graphs, right? Good. Back to this matter here of graphs, right? And the graphs we're talking about is what we call, we'll deal with displacement dash time, right? So some people put displacement with a slash, time graphs, and then there's velocity time graphs, right? Let me, I don't have the right word. Yeah. So we can have what you call displacement time graph. You can have velocity time graph, right? And as I said, there are times depending on the situation where the word displacement can be used interchangeably with distance. Because if you're going in one straight line, right? There are times when, okay, if you're going in a straight line, the distance from here to, let's say, point A to B is the same as the displacement, right? So at that time, you can use this word displacement and distance interchangeably, right? Similarly, if you were going to find the speed that an object moves from here to here in this one direction, it will be the same as velocity because you're dealing with one direction, no change in direction. So speed and velocity sometimes can be used interchangeably depending on the situation, right? Good. So let's talk about these graphs, right? And when you think of displacement time graph, basically it's a graph where you plot the movement of an object, where on the horizontal axis you plot time, and on your vertical axis you plot displacement, right? And I think I promised you an interesting story. Did I? Did I tell you that story with Usain? Yeah. Did we talk about Usain Bolt?
Oh,
That
Sir, I'm
sorry.
not sure if I can recall.
oh you all okay, good. I'll tell you a story
Sir,
quickly about
sir,
how
sorry, they talk about Usain Bolt. Can you give an example when he running from, you checking the speed?
oh well, all
It
right.
was
Let me repeat it for the benefit of
good.
so talking about displacement time graph, right? And as I said, you can use displacement and distance if you're running in a straight line. And you say 100 meters is a straight line. So what I noticed about Usain, right? And they didn't, at first they didn't. All of you know Usain, he's a slender guy, right? You all know him, he's tall and slender. Anybody remember that? Tell me if you know him and so.
Yes, sir.
Yeah, he's a
Yes, sir.
tall and slender guy. And because he's tall and slender, the biology, right? The common knowledge, like those Kenyans, those Kenyan guys, they're very thin. They're very thin, and because of that, their muscles they don't have a lot of fast twitch muscles. They have what you call slow twitch muscles, and they can run a lot of distance because when they're running distance, they get the chance to breathe. Isn't that so? You get time to breathe when you're running marathon and so you gap and you whatever you were running slow, so your muscles you're able to the muscles are able to respire, to burn glucose and whatnot and so on. You can take in air and produce more energy because you're not running fast. You're not demanding too much from your muscle cells, right? So when I watch you say, they say, man, this chap, he's more fit for distance. And some of you may know that Usain used to run like 400 and 800 meters. They used to have him running the longer race because the stereotype or one would think that if this guy is fine and tall, he's more suited for distance or longer distances. But when I don't know if it was his trainer, his manager, somebody figured out that when they watch Usain and they plotted how he was this displacement or the distance he's running in against time, they noticed something. They noticed that this force part, let's say the force, I'm a little wrong there. Let's say the force 100 meters, right? What am I saying? Force 100 meters. This is where the 100 should be. Let me erase all this. I think I got the. Oh. Yeah. Let me erase the whole thing. I want to just show you what they observed about him, right? So they found that when he ran, okay, let's go with 100, 200, 300, 400, right? When he ran, this force part here, let's say, all right, he took 1 minute, right? 60 seconds. He ran something like this, right? And what they found out, they noticed that, you notice this force 100 meter. He covered the greatest or the average speed for his force 100 meter was the largest, his average speed then. He was fastest then during the force 100 meter. And afterwards, he started to slow down. You notice more time is elapsing and he's not covering the kind of ground from around here, from around 200, 300. Notice how the graph kind of falter like, right? He's not this speed that he's going at. I'm going to explain this to you just now. The gradient here, the gradient tells you the speed. The gradient of this line tells you the speed. And you will notice the gradient is the greatest from 0 to 100 meters, right? And as a matter of fact, he was doing it like 10 seconds. And they realized that they were wrong about the man, that even though he was tall and slender, his muscles had a lot of fast twitching fibers inside. And therefore, they realized that, you know what, this man is better suited for 100 and even 200 meters. Because from the time you go over to 300 meters, he starts slowing down. See, he starts slowing down. You understand? The gradient here was the greatest, and that's where he made the record, right? He actually did it in under 10 seconds. His 200 meter, well, is a little slower, right? The second 100 is a little slower, right? And then they realize, you know what? This man is better suited for speed. So he defied biology, right? Everybody who thought that, well, a tall, slender guy should be running the distance, Usain is the exception to the rule, right? They should take him and carry him in a lab and study him. Yes, right? And if you watch, you all notice, boys, if you were watching athletics and so, do you notice his competitors like Gatlin and this guy from Canada that won the other day? What is his name? I forgot his name.
Andre de Graaf.
What's his name?
Andre de Graaf.
That's it, right? You notice those guys are a little shorter, they're stockier, and they got big, thick thighs. You notice that?
Thank you.
They're shorter than Usain. But they have their thigh muscles and so very, very huge, because that is the stereotype that, you know, for you to have fast twitch muscles, you have to have a lot of muscle mass, because what happens in the sprint in the 100 meter, remember 100 meters is 10 seconds. Your muscles don't have the time to take in oxygen and burn glucose and release energy and send it back. No. Your muscle don't have time for that. By the time you make the race done. There's no time for breathing. There's no time for, it's almost as you run that race breathless. 10 seconds. Right? So people with a lot of muscle mass in their thighs tend to be more suited for sprints, right? You tell them to run 400, they're burn out. 800, they fall down and die. But as I said, Usain, he defied all the science, right? All we thought that was true, he threw it out the window. Nonsense. Bottom line though, back to our course here. It came from the analysis of his displacement against time. Mind you, don't quote me and say they use the displacement time graph. Whether they're his managers, trainers, and whoever, right? Whether they actually did this kind of analysis with a graph, I am not sure. But they would have noticed, because I don't know if you noticed that when these guys run, right? They would have people timing them, right? They'd have people timing them. So here is the guy they'd have a stopwatch. And when he covers 100 meters, they'll click a watch. Then another one, when he covers 200 meters, they'll click a watch. The olden days, they'll do it with a stopwatch, those little things in their hand. Now, if you watch sports, do you notice that they would have these like cameras, right? And they would have them on a track. mounted right alongside um, where the turf is, where the people are running. Do you notice that? And those things, they move as fast as the runners. Do you notice that when anybody watch sports?
Yes,
And
sir.
those things will actually tell you second by second, right? Up to a millisecond and so, right? Um, as to how fast you are running and how far you have run. And they could take that information and put it on a computer. The computer wouldn't draw a scrolly graph like this. They'll draw a really, really good graph and analyze it for you with AI now. They'll analyze the whole thing. And they will tell you, as a matter of fact, do you know they found a Chinese guy? I don't know. I'm trying to remember his name. They found a Chinese guy who runs faster than you said in that in the 460 meters, not 100, the 460 meters. He runs faster than Usain. So the steepness of the graph in 60 seconds. Or this one here. He runs the 460 meters faster than anyone in the world. And again, he defied again what the whole world thinks, that Chinese people, they're too short and, they can't run sprints. Chinese are not known for running. Chinese are known for gymnastics and, these other things, not for running. But he actually, again, threw all the science out. But let me tell you, if you see how that guy trains and the amount of apparatus all around him, the Chinese, you know them, right? The amount of technology involved in this guy's training, it's amazing. And they found out that he can run faster than Usain, the 460 meters. It is his last 40 meters that he gets in licks every time. Right? If you have YouTube, you can go YouTube some of Usain's races, and you will see a Chinese guy, unknown fella. But those who have actually looked at his training and whatnot, you'll see the 460 meters. The man is the fastest in the whole world. Nobody can run the 460 meters as fast as him. That includes Usain. But there's no race like a 60 meter. There's a 100 meter. So that 40 meter, he just can't manage it. Yeah, these are all very interesting things. And it can turn into, well, think of Usain, the amount of money he made because they discovered that, right? And if I'm to go right back to what they owe it to, displacement time analysis, whether they use graphs or they just use the crude numbers, right? An understanding of these things can mean a lot, I'm coming back, I'm going to get into the graphs some more, right? Yes. So let's talk a little about the displacement time graphs. Displacement time graphs, right? As I said, the graph plots displacement, and this can either be in meters or km, and the time can either be in seconds or hours, right? Good. And you can have displacement time graphs being okay. You can have something like this. All right. Let me question you and see if you're like something like this. What do you think is happening here? If this describes an object, what's happening here? Anybody can say? So time is going, but the displacement isn't changing, is it? So what's happening here? Is this body moving?
If the displacement is constant?
Yeah.
No.
No, yeah, you're right.
There's time going.
Yeah, time is going, but the thing is moving. So if let's say, all right, you're using this as a reference point, right? And okay, here is where you are the observer, and the person is 10 meters away from you. You start a stopwatch, and seconds are going, and the person will move. So as time is moving, that's why the line has to move, right? But it's still at 10 meters. Person didn't move with reference to you, right? You being the timer, right? So you can have a displacement time graph like that. And that is telling you, no, there isn't motion. There isn't motion, right? Good. Then you can have, all right, let's change it up. So let's draw back our axes. And maybe you have something like this now. Straight line. What's happening here? 10, 20, 30, 40. What's happening here? As time is going on, what's happening? So let's say here, right? Person is 10 meters away from the reference point. Here it's 20. Here it's 30. Here it's 40. Here it's 50. The reason why it has to be like this is because you're plotting time, right? You want to say at 10 seconds, all right, let's just say, all right, let me say 1 second. It's 10 meters away. 2 seconds, 20 meters away, right? So what's happening here? Is the body moving? Is it moving?
Yeah.
Yes, it is moving, right? It's moving. And there's something more about its movement. If we were to take the gradient of this straight line here, right? Let's go with, all right, 1, 2, maybe 3, 3, 4, and 5 here, right? If we were to take the gradient of this line, let's take 2 points, maybe 0, 0, 0, 0, and the point 55, right? This point here, 50, sorry, 550. You put a time for us, right? And you were to take the gradient. You were to take this gradient here from here to here, right? So the gradient is equals to 50 minus 0 over 5 minus 0, which is 50 over 5 equals to, what's that, 10? I want you to pay attention to the unit. The numerator is the distance, right, or the displacement. That's measured in meters. And the denominator is time. It's measured in seconds. So you're dividing meter by seconds. So you get meter per seconds or meter over second. And what's this? What's that the unit of? Meter per second.
Speed.
Speed or velocity, right? So what you're seeing, the gradient of a displacement time graph is velocity. It actually gives you the velocity. Is that clear? The gradient of a displacement time graph gives you velocity, right? And if you want to change displacement with distance, the gradient of a distance time graph gives you speed, if you want to change those words up. And that's an interesting fact, because if you were to have, let that sink down a little. When you see you have a straight line as a displacement time graph, when you have a straight line like this with some gradient, right? With some gradient, what this means, because the gradient of a straight line is always the same everywhere, right? Gradient means slope. The slope of the straight line is the same everywhere. Down here, it isn't steeper here than here. Here isn't steeper than here. It's higher, but not steeper, right? Here is not steeper than here. Here is not steeper than here. It has the same slope. It has the same gradient. Therefore, if the gradient is the same, it means that the velocity is constant, right? You see? So whenever you have a displacement time graph that is a straight line, it means that the velocity is constant. Even that one, even that one that we had earlier, like this, the velocity is constant there. The velocity is simply zero. Right? So having a velocity of zero is constant velocity. Right? So once you have a displacement time graph that is a straight line, you can conclude that the velocity is constant. And when velocity is constant, what can you say about acceleration? If there is no change in velocity, what is acceleration? Huh?
Everything is not zero, sir.
Exactly, yes. I like your reasoning. That girl is answering me steady. It's zero because you're not changing speed or you're not changing velocity. So your acceleration is zero. You're moving at a constant velocity. So there's no acceleration. Very good. I like that. Right? I like that. It's nice, two things. I like when you participate, it tells me that you're engaged, you know. If you passively listen and so on, you're not saying anything, you will tend to lose a bit, you know. Right? And secondly, I hope, even though you're gonna have this video and all of that, you must have a book with you, you know, name the book Physics for Well-Being or something, and anything you hear interesting that is worth noting, write it, right? The reason why is that even okay, let's say you're going over back the work. For you to get what I'm saying, you have to watch this whole video to hear me say that when you have a straight line as a displacement time graph, the velocity is constant and therefore acceleration equals zero. You don't know where in the video I said that, right? You will waste a lot of time searching for that. But if you have it written down somewhere, right, you are going to be able to locate it quickly in your notebook and say, you know what, on this page and this page, I do have notes about displacement time graph, which is a 2-page note. You know, you can quickly locate that note. Secondly, note taking is tied to memory, right? It's tied to memory. You see, when you write notes, you tend to remember what we discussed in class. And mind you, I'm not telling you this off the top of my head. There's research to show that making notes help you to remember. Not only remember, it helps you to understand. Because I'm talking all this stuff, right? I'm talking all this thing. And if you have to take all of that, you can't write everything. You have to jot down the main points. So you have to sift out. You have to, all right, I told you the story of you saying, all right, that's entertainment. So you're not going to write all of that down. You don't have to. But when I make a main point, and there's where you don't have to ask me, sort as a main point, right? You have to figure out, you know, this is something that I never knew. This is something worth noting. So you're constantly analyzing, you're constantly trying to make sense, understand the material. And then you having to translate all this talking into just a few words, right? Into just a few words. That takes a lot from you mentally. It really engages you, right? And while I mean, you when you're doing your test, and so you have your notebook there, I can't do nothing. I can't know you have your notebook there. So it's basically you have an open book test, right? You can't consult AI and the internet, but you have your notes right there. And I wouldn't go and kill you and say, hey, you're not supposed to look in your notes. But if you have no notes, you can't go say, oh God, with a video, man, we talk something in the video. Come. And you scrolling through some video to know what I said. Right? So try to have a notebook nearby, you know, and say, all right, I'm gonna take notes for physics in this book here. And when I say something that you think is interesting, right? Not everything I talk about. I talk a lot of trivial things and so, right? Tell a lot of stories. Don't worry all of that. You wait for that little bit that is worth noting, right? It's worth noting, and you take it down, right? So yeah, engage with me, man. Stop, talk to me, and so yeah, good. What about if you have a displacement time? All right, I'm gonna just write displacement time graph, and maybe it's something like this. Now the gradient here is different from the gradient there. It's different from the gradient there because here it's a less sloping, not so? So let's call this V1, right? At this point, the gradient here is V1, the gradient here is V2, the gradient here is V3, right? So now V1 is a little less than V2, is a little less than V3, that's all. So the body is increasing in velocity. So question, is it accelerating now? Is it accelerating?
I believe it's moving. I think it's moving a little bit faster with less time.
Once it's going
what
up,
do you say? What do you call that? What do you call that? It's what?
acceleration.
Very good. It is accelerating. Yes. It is accelerating. Right? So because it's the velocity is changing, whether it's increasing or even decreasing. Remember we said decreasing acceleration is called deceleration. Remember that? So acceleration can be negative, right? Negative acceleration is called deceleration, right? It's called deceleration. There are times when negative acceleration is not necessarily deceleration. For a falling object, if you take downwards as negative, right? Let's take G. If a body is moving down with minus 9.8, it's not decelerating, right? It's not decelerating, right? So in this case, negative acceleration is not deceleration, right? It's not deceleration. It's how you treat the upward and downward motion. But when something is slowing down, that's deceleration. And very often it shows up in the calculation as negative acceleration. But leave that aside. Our point here is that the fact that this thing is actually speeding up because the gradient is getting greater. The thing is accelerating. Right? On the other hand, if the gradient is getting less, let me draw one like that, right? Let me draw one like that. Let me take out all of this. I want to confuse you with anything heavy. Good. So let's change up this graph. You notice how this one look, right? What about a graph looking like this? It's going this way. So here, the gradient is very steep, right? The gradient is high here, but down here it's gentler, right? It's gentler. Down here, it's even gentler, right? So what's happening? V1 is greater than V2 is greater than V3, right? So there is actually a slowing down happening, not so? Remember, the gradient is the velocity. So down here, the V1 it's moving at the fastest, right? Right? Down here, it's kind of slowing up. It slows up here because V2, the gradient here is less than this. And down here is almost like you're not moving at all, right? You're barely moving. So in this case, you are slowing down, right? You are decelerating, right? The reason why is that you are decreasing in velocity. You are decreasing in velocity. So you are decelerating. Think you get that?
Yes, sir.
Good. Now, the next thing is that sometimes you can't figure out whether you are actually experiencing what we call a uniform acceleration and the motion equation will apply, or you have a uniform deceleration. It's difficult for you to pick that up from the graph, but I'll leave that for more maybe advanced work. Or if we have, maybe we have numbers like, okay, let's just see. From here, let's say this is 1 second. Let's say this is, let me move it up. Let me move this a little closer here. Let me move V2 here, right? I'll erase those. I want to just show you something. Um, 1 second, just want to show you something. So let's put them equally spaced, right? So down here is 2, and let's go here, down here is 3, right? So if you were to find the average velocity from here to here, and then the average velocity from there to there, and the average velocity from there to there, you could actually now figure out what's the acceleration from in the 4 seconds. And then what's the acceleration during the 2nd second? And what's the acceleration during the 3rd second? And now you can decide, you know what, the acceleration is not the same, or it might be the same, right? If it's not the same for each 1 second interval, then you don't have uniform acceleration. But if the average acceleration for each second is the same, well, then you can conclude that, you know what, we have uniform acceleration, right? It's a bit harder to just watch the graph and to figure it out, right? But with actual numbers, yes, you can calculate and make that that decision as to whether uniform acceleration is taking place or whether the acceleration is non-uniform. But I'm not gonna, that's a bit of advanced work, right? I'm having a difficult time trying to make things or keep things simple. I'm having some difficulty there. I must accept. Good. So let's move to what we refer to as the velocity time graph, right? And this one, basically what you do, you plot the velocity here and you plot the time here, right? Most of the time is what we call the independent variable, right? Whenever you're plotting graphs, you plot the independent variable on the x-axis or the horizontal axis, and the dependent variable on the y-axis or the vertical axis, right? Good. And again, the velocity time graph can be, okay, flat like that, right? And What that should tell you?
There's constant velocity.
Very good. Yes. Yes. You're moving at a constant pace, you know? No acceleration. You just maybe you have your vehicle and you have it at 50 and you're just keeping it there. It's hard to do that, right? In reality, constant velocity is very, very difficult to I mean in the real world every day here, right? In space, it's easier, right? Once they achieve a certain velocity, a body can move at that velocity without changing, right? Why? Because in space, there's no all this resistance and all of that, right? But when you're in a vehicle, somebody was going to say something, you can go ahead. Yeah. You're in a vehicle, it's hard to keep your foot on that pedal and keep that vehicle at one speed, right?
Yes, sir.
Yeah, very, very difficult. Constant velocity is hard to achieve, right? Yeah. Good. So let's change it up a little. So we talked about, all right, it's like that. And of course, if the velocity is constant, is there acceleration? Is there acceleration?
No, sir.
No,
No.
there is no acceleration. And another thing you can pick that up from, I'm going to show you just now, the gradient of the velocity time graph, and that's something worth knowing. The gradient of the velocity time graph is acceleration. And the gradient of this flat line graph, right? Gradient equals 0 because there's no slope. Remember, gradient carries the thought of slope. And this graph has no slope, it's a flat line. So because the gradient is 0, the acceleration equals 0. And I'll show you why we are saying that the gradient of the velocity time graph is equal to acceleration. I'll show you that from the units just now. Let me change up this graph. Change up this graph. Change it. Right? So let's say you have a straight line. Right? Now your velocity is changing from time to time now, right? As time go by, the velocity is increasing while time is increasing, right? So that should tell you, yes, there is an acceleration, right? Now, how do we know that? Look, let's take the origin. And let's say down here is 10 seconds and down here is 60 meter per, let's go with km per hour, no, meter per second, right? We go with seconds here, right? T in seconds, velocity in meter per second. So if we were to find the gradient, right? 0, and let me go with, 60, they're too high up. All right, let me put it 10 here. Don't worry, 10 here. Put it 10. So the gradient of this line is equals to 60 minus 0 over 10 minus 0, right? So let's put in the unit. The numerator is in meter per second and the denominator is in seconds. So your answer is going to be 6 meter per second square, right? Notice that it's meter per second divided by second, which is meter per second multiplied by 1 over second, which is meter over second square, right? Which is this. And this here is the unit for acceleration. And that is why we are saying that a gradient of a velocity time graph gives you the acceleration. A gradient of a velocity time graph gives you the acceleration of the body. Now that we have that in mind, this is a straight line, so the gradient is constant all over. So what can you say of the acceleration of this body? What can you say? It's accelerating, yes. But what can you say about the acceleration? What word can we use to describe it?
It's constant and positive.
Very good, yes. It's constant right? It's uniform. And yes, in this case, it's a positive number, right? It's a positive number. Is that clear, right? So we found out there that the gradient of the velocity time graph gives you acceleration, right? It can give you deceleration as well, right? If it's negative. If the gradient is negative, you are decelerating. That's all. Good. So one more thing before I leave off this straight line graph. Let me draw another one, just for, I don't want to confuse you. Let me get another one. And then we'll go when the graph is curved and so, Let's look at this. Okay, let's say take this velocity time graph. V and T, right? And let's say arch, it's a nice straight line like that. And let's say down here is, okay, 10 seconds. We go into 60 there again. And let's take this area here. Let's take the area, right? So the area is going to be what? Well, there's a formula like, right? Area equal, what is it? Half times the base times the height or something like that. So it's going to be half, in this case, half times 10, which is the base, times 60. So it's going to be 5 by 60 is how much? 300? 300, right? But I want to show you something with the unit. This time is in seconds, and this here is in meter per second. So you would have seconds multiplied by meter per second. So watch this. If I put this over 1 and I cancel this second and that second, the unit becomes meters. See that? What you're figuring out there is that the area under a velocity time graph gives you the distance traveled. You see? So we found the area. The numbers, okay, sure, now 300. But when we analyze the units, because we multiply seconds by meter per second, the 2 seconds will cancel out and you're left with meters. So that tells you, right? All of this is something in physics, they call it dimension analysis, right? It helps us to see that, you know what? The area under the velocity time graph gives you the distance traveled by the object, right? And that's something worth jotting down somewhere again, right? Don't search through the video for that. Get a paper, write it down. And don't depend on your memory at all, especially with, with all this smartphone and computer usage and internet access and AI. Our memory has gotten very weak, and that's very
Sir,
bad for us. Yeah.
sir, excuse me. Sir, please
Yeah.
repeat about the definition for area that you just gave.
The area under the velocity time graph, the area under the velocity time graph gives the distance traveled by the object. The textbook might use a fancy word. It will yield, right? I'm just replacing it, that it will give you the distance traveled.
Sir, could you write the definition on the screen, please? Thank you.
No, I wouldn't do it, sir. I want you to, you got to develop that ability to listen and understand and put it in your own words, right? I'm going to repeat it, right? And that's a thing. I'm not belittling you in any way. I'm telling the class, y'all develop that ability to, when you hear stuff, analyze it and put it in your own words, right? So you want to, different people write it differently. Area under velocity time graph equal distance travel, right? Well, as we said, distance and displacement is kind of used interchangeably if we're dealing with one straight line motion, right? It's the distance traveled. So this is a mathematical way of putting it down, right? Another person will write it out in a paragraph. Right?
Right, sir.
Area under velocity time graph equal distance traveled. Yes, yes.
Yes, sir. Just one quick question. So it says area equals a half times the breadth and the height. Half of what? You're halving
Oh,
the time.
this is a oh, you see the maths beating all of them like, oh my. This is a triangle, right? And there's this formula that says the area of a triangle. Good thing you asked the question, right? Good thing you have asked the question. Area of a triangle is equals to half of the base by the height. So the base is like this bottom here, 10, right? And the height is 60, right? You see up here, 60? So down here is 60, right? So half of the base by the height. Friday, I think we did quite a bit today. Friday, we're going to do some more harder examples where the area is not always this nice triangle. It's going to be a trapezium and so. We get into that. No, not today. Not today. Today, you're tax already. Yeah.
So you said harder?
A little harder. Don't worry, man. Don't worry. It's about the brain development, you know. Even if you don't ever use any one of these things, right? That mental activity is good for us. No matter which job you're at, right? The minute you see you go year after year and you don't do nothing mentally, right? You don't do a refresher course and so, you get lackadaisical, right? You're a policeman and they, you know, they ain't do no training, they ain't do nothing for you. All you doing, you just, soon when people walk in the station, you're being like, what a guy named Kunchi and everybody, you start behaving like them. But when you get a refresher course and you know, people talk about public relations and the way to talk to people and you know, the way to deal with the public, and police is not about harassing people, but it's about, you know, service and about helping people and you know, you come to realize, you start to look back at yourself. Is there any police in the room? Any police? No police. Oh gosh, I'm talking in the ear. All right. I think somebody mentioned
We
there
got
were.
police, sir. We got police.
Oh, we got police. Yes. You know, when you go to that refresher course and they talk to you about this, and you come back on the road and you're a much nicer guy. You're more loved by the public. When you're going to ask people things, say, man, you know, something, some certain things went down here. People are willing to talk to you. But if you're harassing people, as soon as them people see you, sir, that if the man run for that side and say, hey, man run for that side and get you gone down some street with some they dig a big hole for you fall in. You know? So yes, a refresher course helps. Nurses, you know, sometimes they fall into this rut. I'm not trying to offend any of the nurses and the medical people. You know, they have no refresher course and so happening. So what happened to them? They get lackadaisical, you know, and they treat the public anyhow and so.
That's
But when you get,
incorrect.
huh?
So that's incorrect with the nurses because we're doing continuous license assessment and we're part of courses every single month.
But
Every
that's what I'm
year.
saying. Yes, that was if there's nothing like that, you know what would happen. Yeah, that's what I'm saying. I'm not saying there is no. I'm just saying that if a nurse, if a police, if a teacher doesn't do progressive training and what you call staff development, and you know, if they don't do anything professional development, that's a more general term. If they don't do any professional development, they'll fall into a rut. You know. So yeah, no, I'm not saying that the nurses don't have it. Yes, that's a good thing, right? It keeps you on your toes. It keeps you learning. Now that I like that a nurse talk about today. I watch a show. I don't know if you all watch this show named Watson. Watson. There's a guy. He's very popular name. What is his name, man? I'll give you his name just now. So there's this batch of doctors, and there's specialist doctors and so. And after when they'd finish their normal rounds, they'll gather in this room and they'll brainstorm you know, the symptoms of a patient, and they'll talk about the treatment from here on. And, you know, they're constantly, you know, kind of developing themselves and developing their knowledge and so, right? And I like that. And I think that that is what should happen. I mean, and you are rightly saying that, yes, there is constant training for you. That's good, right? That's good. Same thing, I think of the police. You know, maybe even watching Law and Order, I will tell you, you really need to improve policing in this country, right? So what I'm saying is constant development is very good, right? Even if what you're studying is unrelated, the mental development that is going to happen and what it pushes you to do, you know. If you can learn a little bit of physics, you can learn anything. If you can learn a little bit of mathematics, you can learn anything, right? So this, as my friend says, is going to get harder. It's good. That's a good thing, right? That's a good thing. If you just you're exposed to stuff that you know already, all you're gonna say, I know it already. You know, here waste time and talk, right? But if you see something new, you say, what? I never think about this. I never know that. It's good every day of your life if you learn something, right? So don't shun away from harder things, from new things, right? And the thing isn't hard. The thing is just new, right? The thing is just new. Let me just touch before our time is catching up with us, right? You all engage in conversation. You know, don't feel I'm not trying to embarrass anybody. And if you object and you say like Norcy just now said, I'm sorry, you're wrong, or we do have progressive training. And that's nice. Yes, I'm happy to know that that's happening, right? Okay, we lost him. All right, let me close with this. You can have a velocity time graph that is either curved that way. It's not a straight line now, right? It's a curve. Let me make it look like a curve. I'd have to edit this video.
Yeah, the fence.
Yeah, somebody got to mute themselves there. Yeah, like if you have a curve, and you can have a curve looking like this too, right? So what's happening here, if this is velocity, this is time, right? Same thing here, right? Here. Your velocity here, sorry, your gradient here, and your gradient here is different. And therefore, you're not moving at constant velocity. You're not uniformly accelerating here. So V, the gradient here, which is, okay, A1, A2, and A3, right? Remember, A1 is a gradient of the tangent here, right? The gradient of the tangent, the gradient of the tangent, the gradient of the tangent. A1 is less than A2 is less than A3, right? So your acceleration is not uniform. Same thing here, right? Here, your acceleration here, A1, A2, A3. A1 is greater than A2, is greater than A3. So you're not dealing with uniform acceleration. It's varying. And these are more complex situations. I'll try to avoid them, but I just want you to be aware, right? I just want you to be aware of this type of scenarios with velocity time graphs. What we'll do Friday, we're going to take some actual problems that involve displacement time graphs and velocity time graphs and see if we can solve, you know, practical problems that we might encounter, right? I know we deviated a lot this evening. I have to do some editing. Yeah, but I always advise, you know, that personal and professional development is never waste, right? Never wasted, right? Once you're bettering yourself, you're bettering your status in life. How can that ever be wrong, right? How can that ever be wrong, right? And besides all of this, for me personally, I tell you too, I mean, now is the We had Ramadan, and then there's the Lent season and all of that. Don't forget spirituality as well, right? Because while some people might be pursuing, more materially and all of that, some people say, well, look, if you're a spiritual person, if you don't, get all the material things that others are trying to get in other ways, you can still be content. You can still be happy, right? You don't have to have a high position. You don't have to have all the knowledge in the world. You don't have to have all the money in the world to be happy, right? And all of that. So spirituality helps with all of that, right? So balance all your other pursuits with, your spiritual life. I mean, if you don't believe in God and all of that, well, that's a different matter. But those are important things as well, right? Not just your upward mobility all the time in the world and you neglect these things. Right? As there's a scripture say you can gain the whole world and you end up losing your life. All right. We will continue this Friday, right?
All right, sir. Good night.
Yes, y'all have a good night, right?
Yes, sir. Good night.
Good night,
See
sir.
y'all. Yeah.